Class 11th Unit Thermodynamics. Chemical energy stored by molecules can be released as heat during chemical reactions when a fuel like methane, cooking gas, or coal burns in air. The chemical energy may also be used to do mechanical work when a fuel burns in an engine or to provide electrical energy through a galvanic cell like dry cell. Thus, various forms of energy are interrelated and under certain conditions these may be transformed from one form into another. The study of these energy transformations forms the subject matter of thermodynamics. The law of thermodynamics deal with energy changes of microscopic systems involving a large number of molecules rather than microscopic systems containing a few molecules. Thermodynamics is not concerned about how at what rate these energy transformations are carried out, but is based on initial and final states of a system undergoing the change. Law of thermodynamics apply only when a system is in equilibrium or moves from one equilibrium state to another equilibrium state. Macroscopic properties like pressure and temperature do not change with time for a system in equilibrium state. In this unit, we would like to answer some of the important questions through the thermodynamics, like how we determine the energy changes involved in a chemical reaction process. Will it occur or not? What drives a chemical reaction process? To what extent do the chemical reactions proceed? Thermodynamic terms. We are interested in chemical reactions and the energy changes accompanying them. For this, we need to know certain thermodynamic terms. These are discussed below. The system and the surroundings. A system in thermodynamics refers to that part of universe in which observations are made and the remaining universe constitutes the surroundings. The surroundings include everything other than the system. System and the surroundings together constitute the universe. The universe is equal to the system plus the surroundings. However, the entire universe other than the system is not affected by the changes taking place in the system. Therefore, for all practical purposes, the surroundings are that portion of the remaining universe which can interact with the system. Usually, the region of space in the neighborhood of the system constitutes into surroundings. For example, if we are studying the reaction between two substances A and B, kept in a beaker, the beaker containing the reaction mixture is the system and the room where the beaker is kept is the surroundings. Note the system may be defined by physical boundaries like beaker or test tube, or the system may simply be defined by a set of Cartesian coordinates specifying a particular volume in space. It is necessary to think of the system as separated from the surroundings by some sort of wall, which may be real or imaginary. The wall that separates the system from the surroundings is called boundary. This is designed to allow us to control the keep track of all movements of matter and energy in or out of system. Types of the system. We further classify the system according to the movement of matter and energy in or out of the system. Open system. In an open system, there is exchange of energy and matter between system and surroundings. The presence of reactant in an open beaker is an example of an open system. Here the boundary is an imaginary surface enclosing the beaker and reactants. Closed system. In a closed system, there is no exchange of matter, but exchange of energy is possible between system and surroundings. The presence of reactant in a closed vessel made of conducting material, example copper or steel, in an example of a closed system. Isolated system. In an isolated system, there is no exchange of energy or matter between the system and the surroundings. The presence of reactants in a thermoflask or any other closed insulated vessel is an example of an isolated system. The state of the system. The system must be described in order to make any useful calculations by specifying quantitatively each of properties such as its properties, volume and temperature, as well as the composition of the system. We need to describe the system by specifying it before and after the change. You would recall from your physics course that the state of a system in mechanics is completely specified at a given instant of time by the position and velocity of each mass of point of the system. In thermodynamics, a different and much simpler concept of the state of a system is introduced. It does not need detailed knowledge of motion of each particle because we deal with average measurable properties of the system. We specify the state of the system by state functions or state variables. The state of a thermodynamic system is described by its measurable or macroscopic means bulk properties. We can describe the state of a gas by quoting its pressure P, volume V, temperature T, amount N, etc. Variables like P, V, T are called state variables or state functions because their values depend only on the state of the system and not on how it is reached. In order to completely define the state of a system, it is not necessary to define all the properties of the system, as only a certain number of properties can be varied independently. This number depends on the nature of the system. Once this minimum number of macroscopic properties are fixed, others automatically have definite values. The state of the surroundings can never be completely specified. Fortunately, it is not necessary to do so. The internal energy as a state function, a quantity which represents the total energy of the system. It may be chemical, electrical, mechanical, or any other type of energy you may think of. The sum of all these is the energy of the system. In thermodynamics, we call it the internal energy, U of the system, which may change when heat passes into or out of the system, work is done on or by the system, matter enters or leaves the system. These systems are classified accordingly as you have already studied. Work. Let us first examine a change in internal energy by doing work. We take a system containing some quantity of water in a thermo flask or in an insulated beaker. This would not allow exchange of heat between the system and surroundings through its boundary, and we call this type of system as adiabatic. The manner in which the state of a system may be changed will be called adiabatic process. Adiabatic process is a process in which there is no transfer of heat between the system and the surroundings. Here, the wall separating the system and the surroundings is called the adiabatic wall. Let us bring the change in the internal energy of the system by doing some work on it. Let us call the initial state of the system as state A and its temperature as Ta. Let the internal energy of a system in state A be called UA. We can change the state of the system in two different ways. One way, we do some mechanical work, say 1 kilojoule, by rotating a set of small pedals and thereby churning water. Let the new state be called B state and its temperature as Tb. It is found that Tb is greater than Ta and the change in temperature del T is equal to del B minus Tb minus Ta. Let the internal energy of the system in state B be UB and the change in internal energy del U is equal to del UB minus UA. Second way, we now do an equal amount electrical work with the help of an immersion rod and note down the temperature change. We find that the change in temperature is the same as in earlier case, say Tb minus Ta. In fact, the experiment in the above manner were done by J.P. Joule between 1840 say 50 and he was able to show that a given amount of work done on the system, no matter how it was done, irrespective of path, produce the same change of state as measured by the change in the temperature of the system. So it seems appropriate to define a quantity, the internal energy U, whose value is characteristic of the state of a system, whereby the adiabatic work WAD, denoted means to say adiabatic work required to bring about a change of state, is equal to the difference between the value of U in one state and that in another state del U. Del U is equal to U2 minus U1 is equal to work done for adiabatic. Therefore, internal energy U of the system is a state function. By conventions of IUPAC in chemical thermodynamics, the positive sign expresses that WAD, work for adiabatic, is positive when work is done on the system and internal energy of the system increases. Similarly, the work is done by the system. Work done of adiabatic will be negative because internal energy of the system decreases. Can you name some of the other familiar state functions are V, P and T. For example, if we bring a change in temperature of the system from 25 degrees Celsius to 35 degrees Celsius, the change in temperature is 35 degrees Celsius minus 25 degrees Celsius is equal to plus 10 degrees Celsius. Whether we go straight up to 35 degrees Celsius or we cool the system for a few degrees, then take the system to the final temperature. Thus, T is a state function and the change in temperature is independent of the route taken. Volume of water in a pond, for example, is a state function because change in volume of its water is independent of the route by which water is filled in the pond, either by rain or by tubal or by both. Heat. We can also change the internal energy of a system by transfer of heat from the surrounding of the system or vice versa without expenditure of work. This change of energy, which is the result of temperature difference, is called heat Q. Let us consider bringing about the same change in temperature, the same initial and final state as before in section 5.1.4a by transfer of heat through thermally conducting walls instead of adiabatic walls. We take water at temperature Ta in a container having thermally conducting walls, say made up of copper, and enclose it in a huge heat reservoir at temperature Tb. The heat absorbed by the system Q can be measured in terms of temperature difference Tb minus Ta. In this case, energy in internal energy del U is equal to Q when no work is done at constant volume. By conventions of IUPAC in chemical thermodynamics, the Q is positive when heat is transferred from the surroundings to the system and the internal energy of the system increases, and Q is negative when heat is transferred from system to the surroundings, resulting in a decrease of the internal energy of the system. The general case. Let us consider the general case in which a change of state is brought about both by doing work and by transfer of it. We can write change in internal energy for this case as del U is equal to Q plus W. For a given change in state, Q and W can vary depending on how the change is carried out. However, Q plus W is equal to del U will depend only on initial and final state. It will be independent of the way that the change is carried out if there is no transfer of energy as heat or as work. Isolated system, if W is equal to 0 and Q is equal to 0, then del U is equal to 0. Del U is equal to Q plus W is mathematical statement of the first law of thermodynamics, which states that the energy of an isolated system is constant. It is commonly stated as the law of conservation of energy. Energy can neither be created nor be destroyed. Note, there is considerable difference between the character of the thermodynamic property energy and that of a mechanical property such as volume. We can specify an unambiguous absolute value for volume of a system in a particular state but not the absolute value of the internal energy. How we can measure the only the changes in internal energy del U of the system. Applications. Many chemical reactions involve the generation of gases capable of doing mechanical work or the generation of heat. It is important for us to quantify these changes and relate them to the changes in the internal energy. Let us see how. Work. First of all, let us concentrate on the nature of a work a system can do. We will consider only mechanical work, pressure, volume work. For understanding pressure volume work, let us consider a cylinder which contains 1 mole of an ideal gas fitted with a frictionless piston. Total volume of the gas as denoted by Vi and pressure of the gas inside is P. If external pressure is P external, which is greater than P, piston is moved inward the pressure. Inside become equal to P external. Let this change be achieved in a single step and final volume of denoted by V. During this compression, suppose piston moves a distance L and is cross section area of the piston is A, then volume change L into A is equal to del V is equal to Vf minus Vi, means final volume minus initial volume. We also know pressure is equal to force per divided by area. Therefore, force on piston Pa external into A. If W is the work done on the system by movement of the piston, then W is equal to force into distance P external into A into L. P external into minus del V is equal to minus P external del V is equal to minus P external into final volume minus initial volume. The negative sign of this expression is required to obtain conventional sign for W, which will be positive. It indicates that in case of compression, work is done on the system. Here Vf minus Vi will be negative and negative multiplied by negative will be positive, hence the sign obtained for the work will be positive. If the pressure is not constant at every stage of the compression but changes in a number of finite steps, work done on the gas will be summed over all the steps and will be equal to minus summation P del V. If the pressure is not constant but changes during the process such that it is always infinitesimally greater than the pressure of the gas, then at each stage of compression the volume decreases by an infinitesimal amount dV. In such a case, we can calculate the work done on the gas by the relation W is equal to minus integration of limit Vf to Vi, final volume to initial volume, P external into dV. P external at each stage is equal to P initial minus plus dP in case of compression. In an expansion process under similar conditions, the external pressure is always less than the pressure of the system. P external is equal to P initial minus dP. In general case, we can write P external is equal to P initial plus minus dP. Such processes are called reversible processes. A process or change is said to be irreversible if here P external at each stage is equal to P internal plus dP. In case of compression in an expansion process under similar conditions, the external pressure is always less than the pressure of the system. P external is equal to P initial minus dP. In general case, we can write P external is equal to P internal plus minus Cp. Such processes are called reversible process. A process or change is said to be reversible if a change is brought out in such a way that the process could at any moment be reversed by an infinitesimal change. A reversible process proceeds infinitely slowly by a series of equilibrium states such that system and the surroundings are always in near equilibrium with each other. Process other than reversible processes are known as irreversible process. In chemistry, we face problems that can be solved if we relate the work term of the internal pressure of the system. We can relate work to internal pressure of the system under reversible conditions by writing equation W reversible is equal to minus integrated V F to Vi P external dV is equal to minus integration from limit final volume to initial volume P internal plus minus dP into dV. Since dP into dV is very small, we can write W reversible is equal to minus limit integration limit from Vf to Vip in internal dV. Now the pressure of the gas can be expressed in terms of its volume through gas equations. For n mole of an ideal gas, PV is equal to nRT. P is equal to nRT by V. Therefore, at constant temperature isothermal process, W reversible is equal to minus integration from Vf to Vi nRT into dV by V minus is equal to minus nRT log n Vf by Vi is equal to minus 2.303 nRT log Vf by Vi. Free expansion of a gas in vacuum is called free expansion. No work is done during free expansion of an ideal gas, whether the process is reversible or irreversible. Now we can write equation 5.1 in number of ways depending on the types of processes. Let us substitute W is equal to minus P external into del V in equation 5.1, and we get del U is equal to Q minus P external into V into del V. If a process is carried out at constant volume del V is equal to 0, then del U is equal to QV. The subscript V is in QV denotes that heat is supplied at constant volume. Isothermal and free expansion of an ideal gas. For isothermal, T is constant expansion of an ideal gas into vacuum. W is equal to 0 since P external is equal to 0. Also, Joule determined experimentally that Q is equal to 0. Therefore, del U is equal to 0. Equation 5.1 del U is equal to Q plus W can be expressed for isothermal reversible, irreversible, and reversible changes as follows. For isothermal irreversible change, Q is equal to minus W is equal to P external into Vf minus Vi. For isothermal reversible change, Q is equal to minus W is equal to nRT log n Vf by Vi is equal to 2.303 nRT log Vf by Vi. For adiabatic change, Q is equal to W. Q is equal to 0. Del U is equal to WAD. Enthalpy H, a useful new state function. We know that heat absorbed at constant volume is equal to change in internal energy del U is equal to QV, but most of chemical reactions are carried out not at constant volume but in flask or test tube under constant atmospheric pressure. We need to define another state function which may be suitable under these conditions. We may write equation 5.1 as del U is equal to Qp minus P del V at constant pressure, where Qp is the heat absorbed by the system and minus P del V represent expansion work done by the system. Let us represent the initial state by subscript 1 and final state by 2. We can rewrite the above equation as U2 minus U1 is equal to Qp minus P V2 minus V1. On rearranging, we get Qp is equal to U2 plus P V2 minus into U1 plus PV1. Now we can define another thermodynamic function, the enthalpy H, as H is equal to U plus PV. So equation 5.1 becomes Qp is equal to H2 minus H1 is equal to del H. Although Q is a path dependent function, H is a state function because it depends on U, P and V, all of which are state functions. Therefore, del H is independent of path, hence Qp is also independent of path. For finite changes at constant pressure, we can write equation 5.7 as del H is equal to del U plus del PV. Since P is constant, we can write del H is equal to del U plus P del V. It is important to note that when heat is absorbed by the system at constant pressure, we can actually measuring changes in the enthalpy. Remember, del H is equal to Qp, heat absorbed by the system At constant pressure, del H is negative for exothermic reactions which involve heat during the reaction, and del H is positive for endothermic reactions which absorb heat from the surroundings. At constant volume, del V is equal to 0, del U is equal to QV. Therefore, equation 5.8 becomes del H is equal to del U is equal to QV. The difference between del H and del Q is not usually significant for systems consisting of only solids and or liquids. Solids and liquids do not suffer any significant volume changes upon heating. The difference, however, becomes significant when gases are involved. Let us consider a reaction. The involved gases, if a VA is the total volume of gaseous reactant, Vb is the total volume of the gaseous products. Na is number of moles of gaseous reactants and Nb is the number of moles of gaseous products, all at constant pressure and temperature. Then using the ideal gas law, we write PVA is equal to NART, PVB is equal to NBRT. Thus PVB minus PVA is equal to NBRT minus NART is equal to RT takes common NB minus NA. P into VB minus VA is equal to RT into VB minus VA. P del V is equal to del NGRT. Here, del Ng refers to the number of moles of gaseous products minus the number of moles of gaseous reactants. Substituting the value of P del V from equation 5.9 in equation 5.8, we get del H is equal to del U plus del NGRT. The equation 5.10 is useful for calculating del H from del U and vice versa. Extensive and intensive properties. In thermodynamics, a distinction is made between extensive properties and intensive properties. An extensive property is a property whose value depends on the quantity or size of matter present in the system. For example, mass, volume, internal energy, enthalpy, heat capacity, etc. are extensive properties. Those properties which do not depend on the quantity or size of matter present are known as intensive properties. For example, temperature, density, pressure, etc. are intensive properties. A molar property, xi m, is the value of an extensive property, xi, of the system for 1 mole of the substance. If N is the amount of matter, xi m is equal to xi by N is independent of the amount of matter. Other examples are molar volume Vm and molar heat capacity Cm. Let us understand the distinction between extensive and intensive properties by considering a gas enclosed in a container of volume V and at temperature T. Let us make a partition such that volume is halved. Each part now has one half of the original volume V by 2, but the temperature will still remain the same T. It is clear that volume is an extensive property and temperature is an intensive property. Heat capacity. In an subsection, let us see how to measure heat transfer to a system. This heat appears as a rise in temperature of the system in case of heat absorbed by the system. The increase of temperature is proportional to the heat transferred. Q is equal to coefficient into del T. The magnitude of the coefficient depends on the size, composition and nature of the system. We can also write it as Q is equal to C del T. The coefficient C is called heat capacity. Thus, we can measure the heat supplied by monitoring the temperature rise provided we know that the heat capacity. When C is large, a given amount of heat results in only a small temperature rise. Water has a large heat capacity. A lot of energy is needed to raise its temperature. C is directly proportional to amount of substance. The molar heat capacity of a system Cm is equal to C by N is the heat capacity for 1 mole of the substance and is the quantity of heat needed to raise the temperature of 1 mole by 1 degree Celsius. Specific heat, also called specific heat capacity, is the quantity of heat required to raise the temperature of 1 unit mass of a substance by 1 degree Celsius. For finding out the heat Q required to raise the temperatures of a sample, we multiply the specific heat of the system C by the mass m and temperature changes del T, as Q is equal to C into m into del T is equal to C del T. The relationship between Cp and Cv for an ideal gas at constant volume heat capacity C is denoted by Cv. At constant pressure, this is denoted by Cp. Let us find the relationship between the two, Cp and Cv. We can write equation for heat Q at constant volume Qv is equal to Cv into del T is equal to del U. At constant pressure, as Qp is equal to Cp into del T is equal to del S. The difference between Cp and Cv can be derived for an ideal gas as for a mole of an ideal gas. Del H is equal to del U plus del into Pv is equal to del U plus del RT is equal to del U plus R del T. Del H is equal to del U plus R del T. On putting the values of del H and del U, we have Cp del T is equal to Cv del T plus R del T. Cp is equal to Cv plus R. Cp minus Cv is equal to R. Measurement of del U and del H calorimetry. We can measure energy changes associated with chemical or physical processes by an experimental technique called calorimetry. In calorimetry, the process is carried out in a vessel called calorimeter, which is immersed in a known volume of a liquid. Knowing the heat capacity of the liquid in which calorimeter is immersed and the heat capacity of calorimeter, it is possible to determine the heat evolved in the process by measuring temperature changes. Measurements are made under two different conditions: at constant volume Qv, at constant pressure Qp. Del U measurements for chemical reactions. Heat absorbed at constant volume is measured in a bomb calorimeter. Here a steel vessel is immersed in a water bath. The whole device is called calorimeter. The steel vessel is immersed in water bath to ensure that no heat is lost to the surrounding. A combustible substance is burned in pure dioxygen supplied in the steel bomb. Heat evolved during the reaction is transferred to the water around the bomb and its temperature is monitored. Since the bomb calorimeter is sealed, its volume does not change. The energy changes associated with the reactions are measured at constant volume. Under these conditions, no work is done, as the reaction is carried out at constant volume. In bomb calorimeter, even for reactions involving gases, there is no work done, as del V is equal to 0. Temperature change of the calorimeter produced by the completed reaction is then heat evolved during the reaction is transferred to the water around the bomb and its temperature is monitored. Since the bomb calorimeter is sealed, its volume does not change. The energy changes associated with reactions are measured at constant volume. Under these conditions, there no work is done as the reaction is carried out at constant volume. In the bomb calorimeter, even for reactions involving gases, there is no work done, as del V is equal to 0. Temperature change of the calorimeter produced by the completed reaction is then converted to Qv by using the known heat capacity of the calorimeter with the help of equation 5.11. Del H measurements. Measurement of heat change at constant pressure can be done in a calorimeter. We know that del H is equal to Qp at constant P, and therefore heat absorbed or evolved Qp at constant pressure is also called the heat of reaction or enthalpy of reaction, del H. In an exothermic reaction, heat is evolved and system loses heat of the surroundings. Therefore, Qp will be negative and del H will be also negative. Similarly, in an endothermic reaction, heat is absorbed, Qp is negative, and enthalpy of reaction will be positive. Enthalpy change, enthalpy of reaction of a reaction enthalpy. In a chemical reaction, reactants are converted into products and is represented by reactant to product. The enthalpy change accompanying a reaction is called the reaction enthalpy. The enthalpy change of a chemical reaction is given by symbol del H. Del H enthalpy of reaction is equal to sum of enthalpies of products minus sum of enthalpies of reactants is equal to summation AI H products minus summation I BI H reactants. Here symbol sigma is used for summation, and AI and BI are the stoichiometric coefficient of the products and reactants respectively in the balanced chemical equation. For example, for the reaction CH4 plus 2O2 into CO2 plus 2H2, HR is equal to summation AiHi H products minus summation BiH reactants is equal to HMCO2 gaseous plus 2HM into H2O liquid minus HM into CH4 gaseous plus 2HMO2 gaseous, where HM is the molar enthalpy. Enthalpy change is a very useful quantity. Knowledge of this quantity is required when our needs to plan the heating or cooling required to maintain an industrial chemical reaction at constant temperature. It is also required to calculate temperature dependence of equilibrium constant. Standard enthalpy of reactions. Enthalpy of a reaction depends on the conditions under which a reaction is carried out. It is therefore necessary that we must specify some standard conditions. The standard enthalpy of reaction is the enthalpy change for a reaction when all the participating substances are in their standard states. The standard state of a substance at a specified temperature is its pure form at 1 bar. For example, the standard state of liquid ethanol at 298 Kelvin is pure liquid ethanol at 1 bar. Standard state of liquid iron at 500 Kelvin is pure iron at 1 bar. Usually data are taken at 298 Kelvin. Standard conditions are denoted by adding the superscript to the symbol del H. Example, del H superscript. Enthalpy changes during phase transformations. Phase transformations also involve energy changes. Ice, for example, requires heat for melting. Normally, this melting takes place at constant pressure, and during phase change, temperature remains constant at 273 Kelvin. H2O to H2O del fusion H superscript is equal to 6.00 kilojoule per mole. Here, del fusion H superscript is enthalpy of fusion in standard state. If water freezes, then process is reversed and equal amount of heat is given off to the surroundings. The enthalpy change that accompanies melting of 1 mole of a solid substance in standard state is called standard enthalpy of fusion. Or molar enthalpy of fusion. Melting of a solid is endothermic, so all enthalpies of fusion are positive. Water requires heat for evaporation at constant temperature of its boiling point Tb and at constant pressure. Amount of heat required to vaporize 1 mole of a liquid at constant temperature and under standard pressure 1 bar is called standard enthalpy of vaporization or molar enthalpy of vaporization. Del vaporization H. Sublimation is direct conversion of a solid into its vapor. Solid CO2 or dry ice sublimes at 195 Kelvin with del sublimation H2 is equal to 25.2 kilojoule per mole. Naphthalene sublimes slowly, and for this del sublimation H is equal to 73.0 kilojoule per mole. Standard enthalpy of sublimation del sublimation H is the change in enthalpy when 1 mole of a solid substance sublimes at a constant temperature and under standard pressure 1 bar. The magnitude of the enthalpy change depends on the strength of the intermolecular interactions in the substance undergoing the phase transformations. For example, the strong hydrogen bond between water molecules hold them tightly in liquid phase. For an organic liquid such as acetone, the intermolecular dipole-dipole interactions are significantly weaker. Thus, it requires less heat to vaporize 1 mole of acetone than it does to vaporize 1 mole of water. Gives values of standard enthalpy, changes of fusion and vaporization for substances. Standard enthalpy of formation. The standard enthalpy change for the formation of 1 mole of a compound from its elements in their most stable states of aggregation, also known as reference states, is called standard molar enthalpy of formation. Its symbol is del HF subscript, where the subscript F indicates that 1 mole of the compound in question has been performed on its standard state for its elements in their most stable states of aggregation. The reference state of an element is its most stable state of aggregation at 25 degrees Celsius and 1 bar pressure. For example, the reference state of dihydrogen is H2 gas and those of dioxygen, carbon and sulfur are O2 gas, C graphite and S rhombic respectively. Some reactions with standard molar enthalpies of formation are as follows. It is important to understand that a standard molar enthalpy of formation del HF is just a special case of del RH where 1 mole of compound is formed from its constituent elements as in above the three equations where 1 mole of each water, methane and ethanol is formed. In contrast, the enthalpy change for an exothermic reaction CaO plus CO2 is to CaCO3 is not enthalpy of formation of calcium carbonate. Since calcium carbonate has been formed from other compounds and not formed from its constituent elements. Also for the reaction given below, enthalpy change is not standard enthalpy of formation. Del FH for HBr, H2 plus Br2, 2HBr. Here 2 moles instead of 1 mole of the product is formed from the elements. Del RH is equal to 2 del FH. Therefore, by dividing all coefficients in the balanced equation by 2, expression for enthalpy of formation of HBr is written as half H2 plus half Br2 to HBr. Standard enthalpies of formation of some common substances are given in table 5.2. By convention, standard enthalpy for formation del FH of an element is reference state. Its most stable states of aggregation is taken as 0. Suppose you are a chemical engineer and want to know how much heat is required to decompose calcium carbonate to lime and carbon dioxide with all the substances in their standard state. Here we can make use of standard enthalpy of formation and calculate the enthalpy change for the reaction. The following general equation can be used for the enthalpy change calculation. Del RH is equal to summation AI del FH product minus summation BI del FH reactants, where A and B represent the coefficients of the products and reactants in the balanced equation. Let us apply the above equation for decomposition of calcium carbonate. Here coefficients A and B are 1 each. Therefore, del RH is equal to del FH is equal to CaO plus del FH CO2 gas minus del FH is equal to CaCO3. Thus, the decomposition of CaCO3 is an endothermic process and you have to heat it for getting the desired products. Thermochemical equations. A balanced chemical equation together with the value of its del RH is called thermochemical equation. We specify the physical state along with allotropic state of the substance in an equation. For example, C2H5OH plus 3O2 to 2CO2 plus 3H2. The above equation describes the combustion of liquid ethanol at constant temperature and pressure. The negative sign of enthalpy change indicates that This is an exothermic reaction. It would be necessary to remember the following conventions regarding the thermochemical equations. The coefficient in a balanced thermochemical equation refer to the number of moles of reactants and products involved in the reaction. The numerical value of del RH refers to number of moles of substances specified by an equation. Standard enthalpy change del RH will have units as kilojoule per mole. To illustrate the concept, let us consider the calculation of heat of reaction for the following reaction. Fe2O3 plus 3H2 to 2Fe plus 3H2. Note that the coefficient used in this calculation are pure numbers, which are equal to respective stoichiometric coefficients. The unit for del RH is kilojoule per mole, which means per mole of reaction. Once we balance the chemical equation in a particular way as above, this defines the mole of reaction. If we had balanced the equation differently, for example, half Fe2O3 plus 3 by 2 H2 to Fe plus 3 by 2 H2, then this amount of reaction would be 1 mole of reaction, and del RH would be del FH2 is equal to 3 by 2 into minus 285.83 kilojoule per mole minus 1 by 2 into minus 824. If we had balanced the equation differently, for example, half Fe2O3 plus 3 by 2 H2 to Fe plus 3 by 2 H2, then this amount of reaction would be 1 mole of reaction, and del RH would be del FH2 is equal to 3 by 2 into minus 285.83 kilojoule per mole minus 1 by 2 into minus 824.2 kilojoule per mole is equal to minus 428.7 plus 412.1 into kilojoule per mole is equal to minus 16.6 kilojoule per mole, half del RH1. It shows that enthalpy is an extensive property quantity. When a chemical reaction is reversed, the value of del RH is reversed in sign. For example, N2 plus 3H2 is equal to 2NH3. Del RH is equal to minus 91.8 kilojoule per mole. 2NH3 to N2 plus 3H2 del RH is equal to plus 91.8 kilojoule per mole. Has law of constant heat summation. We know that enthalpy is a state function, therefore the change in enthalpy is independent of the path between initial state reactants and final state products. In other words, enthalpy change for a reaction is the same whether it occurs in one step or in a series of steps. This may be stated as follows in the form of Hess law. If a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reactions into which the overall reaction may be divided at the same temperature. Let us understand the importance of this law with the help of an example. Consider the enthalpy change for the reaction C graphite plus half O2 to CO. Although CO is the major product, some CO2 gas is always produced in this reaction. Therefore, we cannot measure enthalpy change for the above reaction directly. However, if we find some other reactions involving related species, it is possible to calculate the enthalpy change for the above reaction. Let us consider the following reactions: C graphite plus O2 to CO2. Del RH is equal to minus 393.5 kilojoule per mole, equation first, and CO plus half a O2 to CO2. Del RH is equal to minus 283 kilojoule per mole, equation second. We can combine the above two reactions in such a way so as to obtain the desired reactions. To get 1 mole of CO, on the right we reverse equation 2. In this, heat is absorbed instead of being released, so we change sign of del RH value CO2 to CO plus half O2. Del RH is equal to plus 283 kilojoule per mole, equation 3. Adding equation first and third, we get the desired equation C graphite plus half O2 to Cu, for which del RH is equal to minus 393.5 plus 283 is equal to minus 110.5 kilojoule per mole. In general, if enthalpy of an overall reaction A to B along one route is del RH and C graphite plus half O2 to Cu, for which del RH is equal to minus 393.5 plus 283 is equal to minus 110.5 kilojoule per mole. In general, if enthalpy of an oral reaction A to B along one route is del RH and del RH1 and del RH2, del RH3 representing enthalpies of reactions leading to same product B along another route, then we have del RH is equal to del RH1 plus del RH2 plus del RH3. It can be represented as this diagram. Enthalpies for different types of reactions. It is convenient to give name to enthalpy specifying the types of reactions. A. Standard enthalpy of combustion, symbol denoted by del CH. Combustion reactions are exothermic in nature. These are important in industry, rocketry, and other works of life. Standard enthalpy of combustion is defined as the enthalpy change per mole of a substance when it undergoes combustion and all the reactants of end products being in their standard state at their specified temperature. Cooking gas in cylinders containing mostly butane C4H10 during complete combustion of 1 mole of butane, 2658 kJ of heat is released. We can write the thermochemical reaction for this as C4H10 plus 13 by 2O2 to 4CO2 plus 5H2O. Del CH is equal to minus 2658 kJ per mole. Similarly, combustion of glucose gives out 2802 kJ per mole of heat, for which the oral equation is C6H12O6 plus 6O2 to 6CO2 plus 6H2. Del CH is equal to minus 2802 kJ per mole. Our body also generates energy from food by the same oral process as combustion, although the final products are produced after a series of complex biochemical reactions involving enzymes. Enthalpy of atomization, symbol del alpha AH. Consider the following example of atomization of T hydrogen H2 to 2H. Del AH is equal to 435 kJ per mole. You can see that H atoms are formed by breaking HH bonds, hydrogen bonds in dihydrogen. The enthalpy change in the process is known as enthalpy of atomization. Del AH, it is the enthalpy change on breaking 1 mole of bonds completely to obtain atoms in the gas phase. In case of diatomic molecules like dihydrogen, the enthalpy of atomization is also the bond dissociation enthalpy. The other examples of enthalpy of atomization can be CH4 to C plus 4H. Del AH is equal to 1665 kJ per mole. Note the products are only atoms of carbon and hydrogen in gaseous phase. Now see the following reactions. Na to Na solid to gaseous. Del AH is equal to 108.4 kJ per mole. In this case, the enthalpy of atomization is same as the enthalpy of sublimation. Bond enthalpy, symbol del bond H. Chemical reactions involve the breaking and making of chemical bonds. Energy is required to break a bond and energy is released when a bond is required. It is possible to relate heat of reaction to change in energy associated with breaking and making of chemical bonds, with reference of the enthalpy changes associated with chemical bonds, and two different terms are used in thermodynamics. Bond dissociation enthalpy, mean bond enthalpy. Let us discuss these terms with reference of diatomic and polyatomic molecules. Diatomic molecules Consider the following process in which the bonds in 1 mole of dihydrogen gas are broken. H2 to 2H. Del HHH is equal to 435 kJ per mole. The enthalpy change involved in the process is the bond dissociation enthalpy of hydrogen-hydrogen bond. The bond dissociation enthalpy is the change in enthalpy when 1 mole of covalent bonds of gaseous covalent compound is broken to form products in the gaseous phase. Note that it is same as the enthalpy of atomization of dihydrogen. This is true for all diatomic molecules. For example, Cl2 to 2Cl, del ClClH 242 kJ per mole, O2 to 2O, del O double bond OH is equal to 4 to 8 kJ per mole. In the case of polyatomic molecules, the bond dissociation enthalpy is different for different bonds within the same molecule. Polyatomic molecules, let us now consider a polyatomic molecule like methane. CH4, the overall thermochemical equation for its atomization reaction is given below. CH4 to C plus 4H, del AH is equal to 1665 kJ per mole. In methane, all the 4 carbon-hydrogen bonds are identical in bond length and energy. However, the energies required to break the individual carbon-hydrogen bonds in each successive step differ. We can see in these reactions. Therefore, CH4 to C plus 4H del A H is equal to 1665 kJ per mole. In such cases, we use mean bond enthalpy of carbon-hydrogen bond. For example, in CH4, del CHH is calculated as del CH H is equal to half del A H is equal to half into 1665 kJ per mole is equal to 416 kJ per mole. We find that mean carbon-hydrogen enthalpy in methane is 416 kJ per mole. It has been found that mean carbon-hydrogen bond enthalpies differ slightly from compound to compound as CH, CH3, CH2Cl and CH3NO2 etc. But it does not differ in a great deal. Using Hasse bond enthalpies can be calculated. Bond enthalpy values of some single and multiple bonds are given in table 5.3. The reaction enthalpies are very important quantities as these arise from the chains that accompany the breaking of bonds and formation of the new bonds. We can predict enthalpy of a reaction in gas phase. If we know different bond enthalpies, the standard enthalpy of reaction del RH is related to bond enthalpies of the reactants and products in gas phase reactions as del RH is equal to bond enthalpies of reactant minus Mason bond enthalpies of product. This relationship is particularly more useful when the required values of del FH are not available. The net enthalpy change of a reaction is the amount of energy required to break all the bond in the reactant molecules minus the amount of energy required to break all the bonds in the product molecules. Remember that this relationship is approximate and is valid when all substance, reactant and products in the reaction are in gaseous state. Lattice enthalpy. The lattice enthalpy of an ionic compound is the enthalpy change which occurs when 1 mole of an ionic compound dissociates in its ions in gaseous states Na positive Cl negative to Na positive plus Cl negative. Del lattice H is equal to 788 kJ per mole. Since it is impossible to determine lattice enthalpies directly by experiment, we use an indirect method where we construct an enthalpy diagram called Born-Haber cycle. Let us now calculate the enthalpy of Na positive Cl negative by following steps given below. Na solid to Na gases, sublimation of sodium metal, del sublimation H is equal to 108.4 kJ per mole. Second point, Na gases to Na positive plus electron, the ionization of sodium atoms, ionization enthalpy del IH is equal to 496 kJ per mole. Third, half Cl2 to Cl, the dissociation of chlorine, the reaction enthalpy is half the bond dissociation enthalpy, half del bond H is equal to 1 to 1 kilojoule per mole for Cl plus electron to Cl negative. Electron gained by chlorine atoms. The electron gain enthalpy del Eg H is equal to minus 348.6 kilojoule per mole. You have learnt about ionization enthalpy and electron gain enthalpy in unit 3. In fact, these terms have been taken from thermodynamics. Earlier terms, ionization and electron affinity, were in practice in place of above terms. Fifth, Na positive plus Cl negative to Na positive Cl negative. The sequence of steps is shown in 5.1 figure is known as Born-Haber cycle. The importance of the cycle is that the sum of the enthalpy changes around a cycle is zero. Applying Hess law, we get del lattice H is equal to 411.2 plus 108.4 plus 121 plus 496 minus 348.6. Del lattice H is equal to plus 788 kilojoule for NaCl to Na positive plus Cl negative. Internal energy is smaller by 2 RT and is equal to plus 783 kilojoule per mole. Now we use the value of lattice enthalpy to calculate enthalpy of solution from the expression del Sol H is equal to del lattice H plus del hydration H for 1 mole of NaCl. Lattice enthalpy is equal to plus 788 kilojoule per mole and del hydration H is equal to minus 784 kilojoule per mole. Del Sol H is equal to plus 788 kilojoule per mole minus 784 kilojoule per mole is equal to 4 kilojoule per mole. The solution of NaCl is accompanied by very little heat change. Enthalpy of solution symbol del Sol H. Enthalpy of solution of a substance is the enthalpy change when 1 mole of it dissolves in a specified amount of solvent. The enthalpy of solution at infinite dilution is the enthalpy change observed on dissolving the substance in an infinite amount of solvent. When the interactions between the ions are negligible, when an ionic compound dissolves in a solvent, the ions leave their ordered position on the crystal lattice. These are now more free in solution, but solvation of these ions also occurs at the same time. This is shown diagrammatically for an ionic compound AB. The enthalpy of solution of AB del Sol H in water is therefore determined by the selective values of the lattice enthalpy del lattice H and enthalpy of hydration of ions del hydration H as del solution H is equal to del lattice height H plus del hydration H. For most of the ionic compounds, del Sol H is positive and dissociation process is endothermic. Therefore, the solubility of most salts in water increases with the rise of temperature. If the lattice enthalpy is very high, the dissolution of the compound may not take place at all. Why do many fluorides tend to be less soluble than the corresponding chlorides? Estimates of the magnitudes of enthalpy changes may be made by using tables of bond energy and lattice energies. Enthalpy of dilution. It is known that enthalpy of solution is the enthalpy change associated with the addition of a specified amount of solute to the specified amount of solvent at a constant temperature and pressure. This argument can be applied to any solvent with slight modification. Enthalpy change for dissolving 1 mole of gaseous hydrogen chloride in 10 mole of water can be represented by the following equation. For convenience, we will use the symbol aqueous solution for water. Del HCl plus 10 aqueous is equal to HCl dot 10 aqueous. Del H is equal to minus 69.01 kilojoule per mole. The values of H show general dependence of the enthalpy of solution on amount of solvent. As more and more solvent is used, the enthalpy of solution approaches the limiting value. The value is in infinitely dilute solution. For hydrochloric acid, this value of H del H is given above in equation. If we subtract the first equation from second equation in the above set of equation, we obtain del H HCl dot 25 aqueous plus 15 aqueous to HCl dot 40 aqueous. Del H is equal to minus 72.73 minus 72.03 kilojoule per mole. 0. Minus is equal to minus 0.76 kilojoule per mole. This value of del H is enthalpy of dilution. It is the heat withdrawn from the surroundings when additional solvent is added to the solution. The enthalpy of dilution of a solution is dependent on the original concentration of the solution and the amount of solvent added. Spontaneity. The first law of thermodynamics tells us about the relationship between the heat absorbed and the work performed on or by a system. It puts on no restriction on the direction of heat flow. However, the flow of heat is unidirectional from higher temperature to lower temperature. In fact, all naturally occurring processes, whether chemical or physical, will tend to proceed spontaneously in one direction only. For example, a gas expanding to fill the available volume, burning carbon in dioxygen, giving carbon dioxide, but heat will not flow from colder body to warmer body on its own. The gas in a container will not spontaneously contract into one corner, or carbon dioxide will not form carbon and or dioxygen spontaneously. These and many other spontaneously occurring changes show unidirectional change. We may ask, what is the driving force of spontaneously occurring changes? What determines the direction of a spontaneous change? In this section, we shall establish some criterion for these processes, whether these will take place or not. Let us first understand what do we mean by spontaneous reaction or change. You may think by your common observation that spontaneous reaction is one which occurs immediately. Then, when contact is made between the reactants, take the case of combination of hydrogen and oxygen. These gases may be mixed at room temperature and left for many years without observing any perceptible change. Although the reaction is taking place between them, it is at an extremely slow rate. It is still called spontaneous reaction. So, spontaneity means having the potential to proceed without the assistance of external agency. However, it does not tell about the rate of reaction or process. Another aspect of spontaneous reaction or process, as we see, is that these cannot reverse their direction on their own. We may summarize it as follows. A spontaneous process is an irreversible process and may only be reversed by some external agency. Is decrease in enthalpy a criterion for spontaneity? If we examine the phenomena like flow of water downhill or fall of a stone onto the ground, we find that there is a net decrease in potential energy in the direction of change. By analogy, we may be tempted to state that a chemical reaction is spontaneous in a given direction because decrease in energy has taken place, as in case of exothermic reactions. For example, half N2 plus H2 is equal to NH3. Del RH is equal to minus 46.1 kilojoule per mole. Half H2 plus half Cl2 is equal to HCl. Del RH is equal to minus 92.32 kilojoule per mole. H2 plus half O2 to H2O. Del RH is equal to minus 285.8 kilojoule per mole. The decrease in enthalpy in passing from reactant to product may be shown for any exothermic reaction on an enthalpy diagram. Thus, the postulate that driving force for a chemical reaction may be due to decrease in energy sounds reasonable as the basis of evidence so far. Now, let us examine the following reactions. Half N2 plus O2 to NO2. Del RH is equal to plus 33.2 kilojoule per mole. C graphite plus 2S CS2. Del RH is equal to plus 128.5 kilojoule per mole. These reactions, though endothermic, are spontaneous. The increase in enthalpy may be represented on an enthalpy diagram as shown. Enthalpy diagram. Therefore, it becomes obvious that while decrease in enthalpy may be contributory factor for spontaneity, but it is not true for all cases. entropy and spontaneity. Then what drives the spontaneous process in a given direction? Let us examine such a case in which del H is equal to 0. There is no exchange in enthalpy, but still the process is spontaneous. Let us consider diffusion of two gases into each other in a closed container which is isolated from the surroundings. As shown, the two gases, say gas A and gas B, are represented by black dots and white dots. See these diagrams. Diffusion of two gases respectively and separated by movable partition. When the partition is withdrawn, the gases begin to diffuse into each other, and after a period of time diffusion will be complete. Let us examine the process before partition. If we were to pick up the gas molecules from left container, we would be sure that these will be molecules of gas A, and similarly if we were to pick up the gas molecules from right container, we would be sure that these will be molecules of gas B. But if we were to pick up molecules from container when partition is removed, we are not sure whether the molecules picked are of gas A or gas B. We say that the system has become less predictable or more chaotic. We may now formulate another postulate. In an isolated system, there is always a tendency for the system's energy to become more disordered or chaotic, and this could be a criterion for spontaneous change. At this point, we introduce another thermodynamic function, entropy, denoted as S. The above mentioned disorder is the manifestation of entropy. To form a mental picture, one can think of entropy as a measure of the degree of randomness or disorder in the system. The greater the disorder in an isolated system, the higher is the entropy. As far as a chemical reaction is concerned, this entropy change can be attributed to rearrangement of atoms or ions from one pattern in the reactants to another in the products. If the structure of the product is very much disordered than that of the reactants, there will be a resultant increase in entropy. The change in entropy accompanying a chemical reaction may be estimated qualitatively by consideration of the structures of the species taking part in the reaction. Decrease of regularity in structure would mean increase in entropy. For a given substance, the crystalline solid state is the state of lowest entropy. The gaseous state is state of highest entropy. Now let us try to quantify entropy. Now, one way to calculate the degree of disorder or chaotic distribution of energy among molecules would be through statistical method, which is beyond the scope of this statement. Other way would be to relate this process to the heat involved in a process, which would make entropy a thermodynamic concept. Entropy, like any other thermodynamic property such as internal energy U and enthalpy H, is a state function, and del S is independent of path. Whenever heat is added to the system, it increases molecular motions, causing increased randomness in the system. Thus, heat Q has randomizing influence on the system. Can we then equate del S with Q? Weight experience suggests that the distribution of heat also depends on the temperature at which heat is added to the system. A system at higher temperature has greater randomness in it than at lower temperature. Thus, temperature is a measure of average chaotic motion of particles in the system. Heat added to a system at lower temperature causes greater randomness than when the same quantity of heat is added to it at higher temperature. This suggests that the entropy change is inversely proportional to the temperature. Del S is related to Q and T for a reversible reaction. Del S is equal to Q reversible divided by T. The total entropy change del S total for the system and surrounding of a spontaneous process is given by del S total is equal to del S system plus del S surrounding is greater than 0. When a system is in equilibrium, the entropy is maximum and the change in entropy del S is equal to 0. We can say that entropy for a spontaneous process increases till it reaches maximum, and at equilibrium the change in entropy is zero. Since entropy is a state property, we can calculate the change in entropy of a reversible process by del S system is equal to del Q system reversible divided by T. We find that both for reversible and irreversible expansion for an ideal gas under isothermal conditions, del U is equal to 0, but del S total, del S system plus del S surrounding is not 0 for irreversible process. Thus del U does not discriminate between reversible and irreversible process, whereas del S does. Gives free energy and spontaneity. We have seen that for a system it is the total entropy change del S total which decides the spontaneity of the process, but most of the chemical reactions fall into the category of either closed system or open system. Therefore, for most of the chemical reactions there are changes in both enthalpy and entropy. It is clear from the discussion in previous sections that neither decrease in enthalpy nor increase in entropy alone can determine the direction of spontaneous change for these systems. For this purpose, we define a new thermodynamic function, the Gibbs energy or Gibbs function G, as G is equal to H minus Ts. Gibbs function G is an extensive property and a state function. The change in Gibbs energy for the system del G system can be written as del G system is equal to del H system minus T del S system minus S system del T. At constant temperature, del T is equal to 0. Del G system is equal to del H system minus T del S system. Usually the subscript system is dropped and we simply write this equation as del G is equal to del H minus T del S. Thus Gibbs energy change is equal to enthalpy change, temperature into entropy change, and is referred to the Gibbs equation, one of the most important equation in chemistry. Here we have considered both in terms together for spontaneity energy in terms of del H and entropy del S, a measure of disorder. As indicated earlier, dimensionally if we analyze we find that del G has units of energy because both del H and T del S are energy terms, since T del S is equal to K into J by K is equal to K. Now let us consider how del G is related to reaction spontaneity. We know del S total is equal to del S system plus del S surrounding. If the system is in thermal equilibrium with the surrounding, then the temperature of the surrounding is same as that of the system. Also, increase in enthalpy of the surrounding is equal to decrease in enthalpy of the system. Therefore, entropy change of surroundings del S surrounding is equal to del H surrounding divided by T is equal to minus del H system divided by T. Del S total is equal to del S system plus into minus del H system by T. Rearranging the above equation, T del S total is equal to T del H system is minus del H system. For spontaneous process, del S total greater than 0, so T del S system minus del H system greater than 0. Minus into del H system minus T del S system greater than 0 using equation. The above equation can be written as minus del G greater than 0. Del G is equal to del H minus T del S less than 0. Del S system is the enthalpy change of a reaction. T del S system is the energy which is not available to do useful work. So del G is the net energy available to do for useful work and is thus a measure of the free energy. For this reaction, it is also known as the free energy of the reaction. Del G gives a criteria for spontaneity at constant pressure and temperature. If del G is negative, less than 0, the process is spontaneous. If del G is positive, greater than 0, the process is non-spontaneous. Note if a reaction has a positive enthalpy change and positive entropy change, it can be spontaneous when T del S is large enough to outweigh del H. This can happen in two ways. The positive entropy change of the system can be small, in which case T must be large. The positive entropy change of a system can be large, in which case T must be small. The former is one of the reasons why reactions are often carried out at high temperature. Entropy and second law of thermodynamics. We know that for an isolated system, the change in internal energy remains constant. Therefore, increase in entropy in such system is the natural direction of the spontaneous change. This, in fact, is the second law of thermodynamics. Like first law of thermodynamics, second law can also be stated in several ways. The second law of thermodynamics explains why spontaneous exothermic reactions are so common. In exothermic reactions, heat released by the reaction increases the disorder of the surroundings and overall entropy change is positive, which makes the reaction spontaneous. Absolute entropy and third law of thermodynamics. Molecules of a substance may move in a straight line in any direction. They may spin like a top, and the bonds in the molecules may stretch and compress. These motions of the molecule are called translational, rotational, and vibrational motion, respectively. When temperature of the system rises, these motions become more vigorous and entropy increases. On the other hand, when temperature is lowered, the entropy decreases. The entropy of any pure crystalline substance approaches zero as the temperature approaches absolute zero. This is called third law of thermodynamics. This is so because there is perfect order in a crystal at absolute zero. The statement is confined to pure crystalline solids because theoretical arguments and practical evidences have shown that entropy of system and supercooled liquids is not zero at 0 Kelvin. The importance of the second law lies in the fact that it permits the calculation of absolute values of entropy of pure substance from thermal data alone. For a pure substance, this can be done by summing Q reversible by T increments from 0 Kelvin to 298 Kelvin. Standard entropies can be used to calculate standard entropy changes by Hess law type of calculation. Gibbs energy change and equilibrium. We have seen how a knowledge of the sign and magnitude of free energy change of a chemical reaction allows prediction of the spontaneity of the chemical reaction, prediction of the useful work that could be extracted from it. So far, we have considered free energy changes in irreversible reactions. Let us now examine the free energy change in reversible reactions. Reversible under strict thermodynamic sense is a special way of carrying out a process such that system is at all times in perfect equilibrium with its surroundings. Reversible under strict thermodynamic sense is a special way of carrying out a process such that system is at all times in perfect equilibrium with its surroundings. When applied to a chemical reaction, the term reversible indicates that a given reaction can proceed in either direction simultaneously so that a dynamic equilibrium is set up. This means that the reaction in both the directions should proceed with a decrease in free energy, which seems impossible. It is possible only if at equilibrium the free energy of the system is minimum. If it is not, the system would spontaneously change to configuration of lower free energy. So the criterion for equilibrium A plus B, equilibrium C plus D is del Rg is equal to 0. Gives energy for a reaction in which all reactant and product are in standard state. Del Rg is related to the equilibrium constant of the reaction as shows. Gives energy for a reaction in which all reactants and products are in standard state. Del Rg is related to the equilibrium constant of the reaction as follows. 0 is equal to del Rg plus Rt log Nk. Del Rg is equal to minus Rt log K is or del Rg is equal to minus 2.303 Rt log K. We also know that del Rg is equal to del Rh minus T del Rs is equal to minus Rt log K. For strongly endothermic reactions, the value of del Rh may be large and positive. In such a case, value of K will be much smaller than 1 and the reaction is unlikely to form much product. In case of exothermic reactions, del Rh is large and negative and del Rg is likely to be large and negative too. In such cases, K will be much larger than 1. We may expect strongly exothermic reactions to have a large K and hence can go to near completion. Del Rg also depends upon del Rs. If the changes in the entropy of reaction is also taken into account, the value of K or extent of chemical reaction will also be affected depending upon whether del Rs is positive or negative. Using equation 5.24, it is possible to obtain an estimate of del G from measurement of del H and del S and then calculate K at any temperature for economic yields of the products. If K is measured directly in the laboratory, value of del G at any other temperature can be calculated using equation 5.24.